Next electrophilic substitution reaction in phenol is Kolb's reaction. Now what is Kolb's reaction? Phenol is treated with sodium hydroxide. Why does phenol react with sodium hydroxide? Because phenol is what in nature? Acidic in nature. So this shows the acidic nature of phenol. Here actually first phenoxide ion is formed, so that part is not there for you to study. So it will be converted to what? Sodium phenoxide. So O minus Na plus, okay. So you are getting sodium phenoxide. Then this on reaction with carbon dioxide at high temperature and pressure followed by acidification. What you get is, see here the product obtained is OH COOH. That means the electrophilic substitution, already we have discussed, electrophilic substitution reaction takes place in which? Ortho and para position. So here carbon dioxide, it is actually acting as an electrophile. Why? This bond shifts towards oxygen, so carbon gets what charge? Positive charge. So here in phenoxide ion, what is happening? The electron density is increasing in ortho and para position. So the carbon dioxide molecule attacks the ortho as well as which position? Para also. But here I have written the ortho product. Actually the mechanism of this reaction is not there for you to study. So I have written the ortho product, and this one's name will be what? Ortho hydroxy benzoic acid, or it is also known as salicylic acid. Okay. So the major product is ortho. So in all electrophilic substitution reactions where you get ortho and para products, the major product is always what? Para, but in this case the major product is ortho. The reason I will give you. So understood what is Kolb's reaction? Phenol reacts with sodium hydroxide to give you sodium phenoxide, which on reaction with carbon dioxide followed by acidification gives you what? Salicylic acid. That is, phenol reacts with sodium hydroxide followed by reaction with carbon dioxide and followed by acidification gives you ortho hydroxy benzoic acid, that is known as Kolb's reaction. And here we have taken ortho as the major product, and para hydroxy benzoic acid also will be formed, but that is the minor product. Why ortho hydroxy benzoic acid is formed or salicylic acid is formed? Here you see, in this compound what is possible is hydrogen bonding is possible. That is, this type of hydrogen bonding is known as what? Within the molecule the hydrogen bonding is taking place. So it is intramolecular H bonding. It is intramolecular hydrogen bonding. So is it clear? So that is the reason why salicylic acid is the major product, because here intramolecular hydrogen bonding is possible, so the molecule is more stable. So in Kolb's reaction you are getting the major product as what? Ortho hydroxy benzoic acid and not para hydroxy benzoic acid. So what is Kolb's reaction? Reaction of phenol with sodium hydroxide to give you sodium phenoxide. Here this reaction is happening, why? Because phenol is acidic in nature. Then that on reaction with carbon dioxide followed by acidification gives you salicylic acid, and salicylic acid is the major product. Why? Because there is intramolecular hydrogen bonding, so the molecule becomes more stable, and if it is para hydroxy benzoic acid, that hydrogen bonding is not there. So this becomes the major product. Next reaction is Riemann reaction. Riemann reaction. In this case also, see here, phenol reacts with sodium hydroxide and chloroform, a mixture of sodium hydroxide and chloroform. So sodium hydroxide will react where? Here, because of its acidic nature, sodium phenoxide. Now see here, in case of chloroform, the bond is like this. So this electron pair shifts towards chlorine. So carbon gets what charge? Positive charge. Again it is undergoing what type of reaction? Electrophilic substitution. So here the group attacking is CHCl2. Is it clear? And this is actually not stable. This again reacts with sodium hydroxide followed one sodium hydroxide and second is acidification. So here actually how is the reaction happening is here OH, this is what, two chlorine atoms in the same carbon atom is not stable and it is being replaced by OH molecule, and from here a molecule of water is eliminated minus H2O. So actually what are you getting? ONaCHO, got it? And on acidification Na will be replaced by what? H. So the product is what? OHCHO. This is known as salicyl aldehyde, or you can say orthohydroxy benzaldehyde. Is it clear? So somewhat both the reactions are what same only. Here phenol is treated with sodium hydroxide and chloroform. So NaOH reaction is due to its acidic nature of phenol, and then chloroform, it undergoes electrophilic substitution due to greater electronegativity of chlorine atom. The carbon atom gets what charge? Positive charge. And the same carbon atom is having two halogen atom and it is not stable. This is again treated with sodium hydroxide. The two chlorine atoms are replaced by what? OH, and since it is not stable it loses a molecule of water. So you get what? CHO. Then H plus is Y, to replace Na is replaced by H plus. So you are getting salicyl aldehyde or orthohydroxy benzaldehyde. Now see here also which is the major product? Ortho product. Again the reason is same only, due to intermolecular hydrogen bonding. So here also what is possible? Intramolecular hydrogen bonding is possible. So that is the reason why salicyl aldehyde is the major product. So in Rimettimann reaction, when you are using sodium hydroxide and chloroform, the product formed is salicyl aldehyde. Suppose instead of chloroform if you use carbon tetrachloride, the product formed will be salicylic acid. So that is not there in your NCERT syllabus. Is it clear? Kolb's reaction and Rimettimann. See, both are examples of what reaction? Electrophilic substitution reaction. And in case of electrophilic substitution reaction, mostly when you have ortho and para product, the para is the major product because it is more stable, but this is an exception where in case of Kolb's reaction and Rimettimann reaction where you have the ortho as the major product. That is, in case of Kolb's reaction it is salicylic acid, and in case of Rimettimann reaction it is what? Salicyl aldehyde. In both the cases the ortho product is major product. Why? Due to intramolecular hydrogen bonding, because the molecule can form intramolecular hydrogen bond, so they become more stable. Next we will go to is preparation of ethers. The first method which we are going to discuss is from dehydration of alcohol. Already we have discussed in alcohol chapter chemical properties of alcohol. Dehydration of alcohol gives you what? Alkene. Now here you see same reaction writing, see C2H5OH when heated with concentrated sulfuric acid at about 413 Kelvin, it undergoes dehydration and the product is C2H5O C2H5. That means you are getting an ether. What is its name? Diethyl ether. So here also plus water. Water is being eliminated. It is undergoing dehydration, but the product is not an alkene. You are getting a ether, diethyl ether, and it is what type of ether? It is a symmetrical ether or ethoxyethane. And if you take CH3, CH2, CH2OH. This when heated with concentrated sulfuric acid at 413 Kelvin. See, actually her two molecules are reacting, but in NCERT they have not given the number of molecules. So you have to keep in mind it is when 413 Kelvin, how many molecules will react? Two molecules. See here, CH3, CH2, CH2OH. This is one molecule. The second molecule, CH2, CH2, CH3. So what is eliminated? A molecule of water. So what is the product? Again, it is a ether. CH3, CH2, CH2O, CH2, CH2, CH3 plus H2O. So it is undergoing again dehydration only. What is the name of this one? 1, 2, 3. You get 1 propoxy propane. So, in all these cases what are you getting? A symmetrical ether. If you have to get an unsymmetrical ether, you have to take what? Two different alcohols. So, that is one of the limitation of this method, that is by dehydration of alcohol we can prepare only what? Symmetrical ethers. If we have to prepare unsymmetrical ethers, we have to take two different types of alcohol. So, that is not possible. So, that is one of the limitation of dehydration of alcohol to give ether. Now, see here, both the cases have taken what type of alcohol? Have taken primary alcohol only. I did not take secondary or tertiary. Why? Because you know, secondary and tertiary alcohols, when treated with this dehydrating agents, they give you alkene instead of giving an ether. That means instead of undergoing substitution reaction, they are undergoing what reaction? Elimination reaction. Why they are undergoing elimination reaction? Because the order of stability of carbocation is what? Tertiary greater than secondary greater than primary. Because a secondary and a tertiary carbocation is stable, so they can easily lose a proton to give alkene as the major product. That means they undergo what type of reaction? Elimination reaction. So, that is also a limitation of what? Dehydration of alcohol to give you an ether. So, in case of dehydration of alcohol to give an ether, by this method we can prepare only what type of ethers? Symmetric ethers, and the alcohol which we take should be what? Primary. Secondary and tertiary alcohols will not undergo dehydration reaction to give you an ether. Why? Because they proceed by what mechanism? They undergo elimination reaction. Why elimination reaction instead of substitution reaction? Because the carbocations formed, that is a tertiary carbocation and a secondary carbocation are stable. So, they can easily lose a proton to give you what? Alkene as the major product. So, you can't prepare secondary or tertiary ethers by dehydration of alcohol. Is it clear? So, that are the limitations of this method. So, the first limitation is what? Only symmetrical ethers can be prepared. Then the second one, only primary alcohols can be used. Secondary and tertiary alcohols undergo dehydration to give alkene instead of ether, because tertiary and secondary carbocation are stable, so they easily lose proton to form alkene. That means they are undergoing what type of reaction? They are undergoing elimination reaction. Now, when you get an ether means it is what? Substitution reaction. So, secondary and tertiary alcohols, they are undergoing elimination reaction to give alkene as the major product. So, is it clear? So, primary alcohols reacts with concentrated sulfuric acid at 413 Kelvin to give you a symmetrical ether. Secondary and tertiary alcohols cannot be used, and you do not get secondary or tertiary ethers by this method, because they proceed by what reaction? Elimination reaction to give you an alkene, as secondary and tertiary carbocations are more stable. Next we will discuss is the mechanism of this reaction. Next we will discuss is the mechanism of dehydration of alcohol to give ether. Already we have discussed the mechanism of what? Dehydration of alcohol to give alkene. Now dehydration of alcohol to give ether. So the question comes is, write the mechanism of dehydration of alcohol to give ether. In general they can ask, or they may give you a reaction and ask you to propose the mechanism. C2H5OH, concentrated sulfuric acid, at 413 Kelvin gives you C2H5O, C2H5 plus H2. So, this way also they may give you and ask you to propose a mechanism. See, when the temperature is 413 Kelvin and the product is ether, just think that the alcohol which you are taking is excess. That means it is more than one molecule. So, always what is the first step? Acid will dissociate to give you H plus ion, aqueous plus HSO4 minus aqueous, and always a proton is there, means it will go and attack whom? Oxygen atom. So, first step is formation of protonated alcohol. This is the first step. So, you will get C2H5OH, here oxygen is having lone pair. So, it is giving to the proton. So, you are getting what? C2H5OH2, that is protonated alcohol. Now, this is in excess. So, next is one more molecule. So, the next molecule I am writing here CH3 CH2OH, okay, plus this also I am writing it this way, let us split it and write OH. Now, see here, we know oxygen is more electronegative, so this electron pair shifts towards oxygen. So, this carbon is getting what charge? Positive charge. So, this proceeds by SN2 mechanism. So, it is undergoing what type of mechanism? SN2 mechanism. Why? The attack of the nucleophile takes place before the cleavage of carbon halogen bond, that is this nucleophile, that is oxygen is having lone pair, it goes and attacks this carbon atom, that time this bond is shifting towards oxygen. That means it is proceeding by which mechanism? SN2 mechanism. So, when you are taking secondary or tertiary alcohol, it proceeds by which mechanism? SN1. In case of SN1 mechanism, what is the first step? Formation of carbocation, and that carbocation form, that is secondary and tertiary, is more stable. So, it is converted into what? An alkene. So, here it proceeds, in case of primary, it is proceeding by which mechanism? SN2 mechanism. So, the nucleophile attacks the carbon atom before the cleavage of carbon oxygen bond. So, what will be formed? CH3 CH2OH, here what will come? CH2 CH3. So, this oxygen is getting what charge? Positive charge. So, what will be the next step? Deprotonation. So, it is CH3 CH2OH CH2 CH3 with positive charge, shifts here. So, you will get CH3 CH2 OCH2 CH3 plus H plus. So, understood the mechanism? First step is formation of protonated alcohol. Second is it proceeds by which mechanism? SN2 mechanism. So, the nucleophile attacks the carbon atom before the cleavage of carbon oxygen bond, resulting in the formation of a protonated ether, and then next step is what? Deprotonation. The proton is eliminated and you get what? Ether. So, understood? So, that is the reason why primary alcohol gives you ether, because it proceeds by SN2 mechanism. But in case of secondary and tertiary alcohols, they will proceed by what? They are more stable, so they proceed by more number of electron releasing groups. So, they proceed by which mechanism? SN1. So, in case of SN1 mechanism, before the attack of the nucleophile, what is being formed? A carbocation is formed, and since the carbocation, a secondary and a tertiary carbocation is stable, so they can easily lose a proton to give alkene as the major product. So, in this you get reasoning questions, give reason why secondary and tertiary alcohol when treated with an acid does not give you ether, but alkene is the major product. So, the answer what will you write? It is because it proceeds by which mechanism? SN1 mechanism. So, it results in the formation of a carbocation. Tertiary and secondary carbocations are more stable, so they can easily lose a proton to give alkene as the major product. Now, next method of preparation is Williamson synthesis. Now, what is Williamson synthesis is? Sodium salt of an alcohol reacts with haloalkane to give you ether. So, in this reaction what I have taken, both the alkyl groups are same. So, you are getting what, a symmetrical ether. Now, it can be different also. R prime ONA plus RX gives you what? R prime OR plus NaX. So, what is the, in case of Williamson synthesis, you see what is its plus point in this reaction? You can prepare by, in this reaction, both symmetrical as well as unsymmetrical ethers. In dehydration of alcohol, we could prepare only what type of ethers? Symmetrical. In Williamson synthesis, both type of ethers can be prepared, both symmetrical as well as unsymmetrical. So, what is Williamson synthesis? Sodium alkoxide, that is sodium salt of alcohol reacts with haloalkane to give you either symmetrical or unsymmetrical ether. So, that is known as Williamson synthesis. So, sodium salt of alcohol reacts with alkyl halide to give symmetrical oblique unsymmetrical ether. So, that is known as what? Williamson synthesis. So, I am just taking here, you see, CH3 CH2 ONA. What is this compound? It is sodium ethoxide plus CH3 CH2 Cl, any haloalkane you can take. So, what will be the product? NaCl will be eliminated. So, you will get CH3 CH2 O CH2 CH3 plus NaCl. Got it? So, getting a symmetrical ether. Next I am going to take is CH3 CH2 ONA plus CH3 Br. So, here you are going to get what? CH3 CH2 OCH3 plus NaBr. So, this is what? Unsymmetrical ether. So, both are what? Primary only. Now, you can, by this method you can prepare secondary as well as what? Tertiary. So, is it clear? Next we will see is preparation of secondary and tertiary ethers by Williamson synthesis. Now, see here, I am going to write a reaction here, CH3CH CH3 ONA, that is, what is its name? Sodium isopropoxide plus I am taking CH3 CH2 Pr, that is ethyl bromide. Okay. Next I am going to write here CH3 CH2 ONA, that is sodium ethoxide plus I am taking isopropyl bromide. Two reactions I have written here. Is there any difference in both these cases? In this case, what should you get? In the first case, tell me. Here also you should get CH3CH CH3 O CH2 CH3. Okay. And here also what should you get? CH3 CH2 O CH CH3 CH3. So, this should be the product in both the cases. In the first case also, because it is also sodium salt of alcohol, this is haloalkene, this is also sodium salt of alcohol and this is what? Haloalkene. But you see here, in both the cases the products are different. This way if you do, you are not going to get Williamson's product. Here the product is an alkene is the major product. Here you will get an Here the product is CH3 CH CH3 O CH2 CH3. Okay, this is the product, that is Williamson's synthesis. And in this case, the product is not Williamson's product, you get an alkene, that is you are getting what? Propene. So, what is the difference? In the first case you are getting Williamson's product, in the second case you are getting alkene, that is here it is undergoing what reaction? Substitution, here it is undergoing what reaction? Elimination reaction. So, now listen carefully. In case of Williamson synthesis, the haloalkane which you take should be always primary. So, that is what haloalkane taken should be primary. Okay. That is the first thing in Williamson synthesis, the haloalkane taken should be primary. The alcohol part, that is sodium salt of alcohol, it can be secondary or tertiary. What is the reason behind this? We have discussed beta elimination reaction in the first chapter, haloalkenes. Haloalkenes when heated with ethanolic alkali, it undergoes elimination to give you alkene as the major product. Same is the case here also. See here, this is a haloalkane, this is what? Alcoholic sodium ethoxide. So, this acts as a base, and in presence of a base it easily undergoes elimination to give you alkene. Why? The reason again is the same only. Secondary and tertiary carbocations are what? Stable. So, they can easily lose a proton to give you alkene as the major product. Here you see it is what? Primary. So, here the carbocations are not so stable, so that they cannot easily lose a proton. So, they easily undergo what reaction here? Here the reaction is substitution, and in this case the reaction is what? Elimination. So, one of the limitation of Williamson synthesis is that the haloalkane which you take should be always what? Primary. The alcohol, sodium salt of alcohol which you take can be secondary or tertiary, but the haloalkane should be primary. If the haloalkane is secondary or tertiary, it undergoes which reaction? Elimination reaction to give you alkene as the major product, because in presence of a strong base the carbocation can be easily formed and it can easily lose a proton to give alkene as the major product. So, that is the limitation of Williamson synthesis. See, it has got many positive points, that is plus points, that is we can prepare both symmetrical and unsymmetrical ethers, we can prepare secondary as well as tertiary ethers, all that can be done, but the limitation is what? The haloalkene which you take should be always primary. If it is secondary or tertiary, in presence of a strong base it undergoes elimination reaction instead of substitution reaction to give alkene as the major product. So, the haloalkane taken should be always what? Primary. Suppose if I write a reaction here, CH3C, CH3, CH3, Cl plus C2H5ONa. Here what will be the major product in this reaction? Will it undergo Williamson synthesis? This is a tertiary haloalkane, and so this is what, this will act as what? A strong base. So, it will undergo which reaction? Beta elimination reaction. So, this is alpha carbon atom, this is beta, this is beta, this is beta. So, what will be the major product? CH3, C, CH3, double bond, CH2. That means you are getting an alkene. So, if it has to undergo Williamson synthesis, what have you to take? This should be the alcohol part and this should be the haloalkane part. So, how will you write the reaction? CH3, C, CH3, CH3, ONa plus C2H5, Cl. So, in this case what will be the product? CH3, C, CH3, CH3, O, C2H5. So, what is its name? From where will you number? 1, 2, 3. So, its name is 2-ethoxy 2-methyl propane, or what will be its common name? Ethyl tertiary butyl ether, or ethyl tertiary butyl ether. So, is it clear? Williamson synthesis. So, that you have to remember, in case of Williamson synthesis, the haloalkane which you take should be always primary. The alcohol can be either secondary or tertiary.